Hi, I'm Sasha Sachs, and I'll be introducing side tuning, a baseline for network adaptation via additive side networks. Often, instead of training from scratch, we'd like to adapt some existing network to a new task. For example, taking a surface normal estimator and using it to do semantic segmentation. We might want to do this either because of a lack of training data on a new task or to use some previously learned weights or representations as a useful prior. Approaches for network adaptation typically fall into two main categories: freeze the weights and add parameters, with the simplest approach being fixed features, or update the parameters, with the simplest approach being fine-tuning. These two examples have markedly different characteristics in practice. As fixed features don't get updated during training, any information discarded by the features never gets recovered, and this limits final performance. Though if you only have a few samples, this limited final performance might not be a problem. Fine-tuning takes a different approach and updates all the parameters during training. This leads to good long-term performance, but for limited data, it can actually lead to significant overfitting. Side tuning is a straightforward freeze and add approach that seeks to mitigate both of these issues. It consists of a frozen base network, as in fixed features, a side network that gets updated over the course of training for the target task and leads to good long-term performance, and the two are combined by alpha blending, which is just a normalized weighted sum. Depending on the curriculum used for alpha and alpha blending, both fixed features and fine-tuning are special cases. For example, set the value of alpha to 1, and this becomes features. Setting it to 0 makes it become fine-tuning. By decaying alpha over the course of training, side tuning becomes a maximum a posteriori-like combination of the base network as a prior with a side network. In practice, we just learn alpha, but the probabilistic interpretation suggests that for intermediate amounts of data, we might see side tuning outperform both features and fine-tuning. We show this on imitation learning with a denoising base, and for intermediate numbers of expert trajectories, side tuning significantly outperforms both features and fine-tuning. In general, we should expect side tuning to perform as the better of fixed features or fine-tuning. And we see this in practice, showing it in different domains, using different architectures with different amounts of data and different training algorithms. Specifically, we show this with transfer learning and taskonomy on both low and high dimensional prediction tasks using both high and low amounts of data. We show this in the NLP domain, doing question answering on squad with the transformer architecture, and doing navigation using imitation learning, which is in an active POMDP setting and requires sequential decision making. And then using RL instead of imitation learning, which uses PPO instead of supervised learning. Across all these different settings, side tuning is consistently the top performer. In addition to evaluating side tuning and network adaptation, which simply adapts to a single target task and is evaluated only on that target, we test side tuning in incremental learning, where the learner must adapt to a sequence of tasks and is evaluated on all of them at the end. In incremental learning, there are two new considerations. Networks tend to forget information on old tasks, catastrophic forgetting, and as constraints and connections are added, learning slows down, rigidity. Side tuning addresses these naturally so that forgetting and rigidity are not possible. We simply extend side tuning to add a new network for each additional task. This prevents forgetting and rigidity, and we test this in the standardized CFAR environment, which is a partitioning of CFAR 100 into a sequence of 20 5-way classification tasks. We also tested in the more challenging iTaskonomy environment, which we introduce. These tasks are significantly harder and more diverse than ICFAR, and involve both image-to-image prediction tasks as well as fine-grained classification. In fact, our object classification task alone could be partitioned to make 20 5-way classification tasks, just like ICFAR, but the images are significantly more complex. For example, compare the taskonomy images at the top to the CFAR images in the bottom, which always contain a single object in the center of the image and there's little if any clutter. Moreover, the images in CFAR are tiny and are shown actual size in the bottom left of the image here. In multitask learning, trends tend to shift on harder data sets, and methods which work well on simple ones often fail in harder contexts, as noted by Stanley et al. At ICML this year. We see this on iTaskonomy, where methods that work well in ICFAR show significant forgetting in the harder context. For example, in the bottom 3 rows shows EWC, which produces good initial estimates, but as training continues to the right, there's significant forgetting. Side tuning beats state-of-the-art approaches, and it does better on harder data sets. We quantified this by showing loss and error curves for both data sets. The quantification also reveals rigidity. For example, the method shown in maroon here works well initially, but as training continues, becomes progressively worse relative to the other methods. We quantify rigidity as the ratio of the loss on the task when learned in sequence versus the loss if you had instead learned that task first. We take the log of this and show it here. As expected, side tuning shows zero rigidity on both ICFAR and iTaskonomy. In contrast, other methods which work well in ICFAR become increasingly rigid on iTaskonomy. For example, progressive neural networks, which are basically side tuning, but with a bunch of additional connections between the base and the side networks, work well on ICFAR where all the tasks are quite similar, 5-way classification on CFAR. On the more diverse tasks in iTaskonomy, it becomes difficult to tell which of these connections should be used and which should not, making the learning problem harder and slowing down training on later tasks. Because side tuning doesn't have all of these additional connections, it can be applied in more general contexts than most of these other methods. For example, in cases where the base model isn't a network at all. Instead, it could be a decision tree or an oracle for some other task. We experiment with the case where the base model is just a ground truth curvature label. We resize and reshape the curvature label, throwing away information, but making this comparable to the previous approaches. And side tuning with the ground truth curvature label works better than all of the other methods. It even outperformed the other side tuning methods. There's a lot more analysis in our paper too. For example, showing that if your base network is too big to use, you can distill it into a smaller one and use that instead. This is often important for reinforcement learning where there's quite large batch sizes and big models won't fit on a single device or even multiple devices. There's more on our website too, like our code and a Docker so that you can run our experiments on your own machine, and we encourage you to check it out. Overall, side tuning is a simple yet effective baseline for network adaptation. It performs as well as or better than existing state-of-the-art methods, despite being significantly easier to implement and applicable in more general contexts. The simplicity provides a clean scaffold upon which to build improvements, and we suggest a few of them in the paper. Thanks for listening.